Greetings, this is Greg. There are a lot of videos out there about the Avro Lancaster, but I noticed that most of them seem to focus on the relatively few specialized missions flown by modified airplanes. I don't see a lot of them focused on the plane itself or the most common usage of the plane, which was as a heavy strategic bomber that flew sustained attacks night after night. I think the reason for that is because the plane's specialized uses are very exciting to talk about, like the Dam Busters raid in which the Lancaster carried a special weapon in during a very daring attack. It makes for a great video, but it doesn't represent the normal Lancaster missions or crews. On the other hand, night bombing of population centers is something that's just not comfortable to talk about or even hear about, but it is part of the history. I'll plow through that issue later. Side note, there are so many books and videos on this plane, I had to dig pretty deep to find some pictures that haven't been commonly used, so hopefully some of these are new to you. The Avro Lancaster, while a very good airplane, was far from perfect. Its post-war reputation has grown well beyond the plane's actual ability, and I think that matters, because exaggerating the plane's capabilities diminishes the contributions of the crew. As we will see, the Lancaster crews succeeded through skill, bravery, and clever use of the airplane, playing to its strengths and avoiding its weaknesses, not because they were flying in some sort of super bomber. The Lancaster was derived from the twin-engine Avro Manchester. The Manchester had quite a bit of potential but didn't work out all that well. Only about 200 were built, and they were pulled from frontline service after about a year and a half of action. The Manchester was powered by a pair of Rolls-Royce Vulcan engines. These were X-type engines, meaning they were configured as two V-types stuck together, an upright V12 and an inverted V12. I'm going to hugely oversimplify here, but they were more or less a pair of Rolls-Royce Peregrines stuck together. The Vulture engine never reached its potential. In order to keep them reliable, they had to dial power back, which resulted in the Manchester being massively underpowered and still unreliable. Now, it's possible that with time and effort, the Rolls-Royce Vulture could have developed into something fantastic, but there was a war on. The Merlin engine was already well developed. It was proven and ready for action, so it made a lot more sense to convert the Manchester into a four-engine airplane using four Merlins to get the power they needed, so that's what they did. Along with some other changes, this is what became the Lancaster. The Lancaster's wing is mounted relatively high. Some other bombers like the B-17 were in the low-wing configuration, and there were mid-wing airplanes like the A-26. Of course, these are general terms, and sometimes the line between them is blurry. For example, if looked at from the front, the B-24 Liberator appears to be a high-wing airplane. From the rear, it looks like it's mid-wing. The B-24 manual specifically calls it a mid-wing. The Lancaster is a bit like the B-24 in that regard. It sort of blurs the line between mid and high wing. If mid to high wing was a term, that's how I would describe it. Period publications don't seem to mention the wing location, not official publications anyway, although this one, talking about the York, which was derived from the Lancaster, calls it a high wing, so take that for what it's worth. In any case, each type of wing position, low, mid, or high, has its pros and cons, but as we will see, the Lancaster's wing position turned out to be really important. Now, let's look at the tail. It's a twin tail with the horizontal stabilizer extending from the back of the fuselage with relatively small vertical stabilizers and rudders at each end. Why use a twin tail? Well, for the purposes of this discussion, please keep content in mind. We're talking about the tail design of World War II bombers. There are some smaller airplanes designed with this type of tail for aesthetic reasons, and there are a lot of modern military aircraft that use it because two small vertical sections reduces the radar cross-section as compared with one big one. And sometimes they go with twin tails because it enables them to tilt them outwards to increase rudder authority at very high angles of attack. The FA-18 is a good example of the latter. In terms of World War II bombers, this design has two big advantages over a single tail. It increases the effectiveness of the rudder behind an operating engine due to the propeller's accelerated slipstream. Remember, the Lancaster's airframe was originally a twin engine, so in the event of an engine failure, the rudder behind the operating engine would have increased authority. It's not a coincidence that the vertical stabilizers and rudders in the Lancaster are directly behind the inboard engines, which is of course where the only engines were in the Manchester. Another advantage is that it gives the upper turret gunner an improved field of fire to the rear. In a single-tail design like the B-17, the ability of the upper turret to protect the plane from attacks from the rear is hindered by that tall vertical stabilizer. Of course, the B-17 is a low-wing airplane. Now, if you start looking at World War II bombers, you'll notice that it's very unusual to have a low-wing airplane with a twin tail. They are almost always high-wing or mid-wing. Let's look at some examples. The Dornier 17 has a similar tail, and it's a high wing. Same with the later Tu-17. The Me-264 is the same way, again a twin tail, high wing. Not many of these were built, but we're talking about the principle here. The Ju-88 has a single tail, and it's a low wing, maybe mid-wing from some angles, but when they designed the Ju-288, they made it a high wing, and notice it then got the twin tail. With U.S. airplanes, it's much the same. The B-24 is officially a mid-wing and has a twin tail. The B-25, clearly not a low wing, has a twin tail as well. As a general rule, if it's a World War II medium or heavy bomber with a twin tail, it's not a low-wing airplane. Now, there are a few exceptions to this general rule. The Soviet PE-2 comes to mind, but it's a much smaller airplane. Its maximum takeoff weight is about 26% of a Lancaster or a B-17's. Now that I think about it, it's about the same weight as a heavier U.S. fighter like a heavily loaded P-38 or P-47, so it's certainly no medium bomber. The PE-2 is more of an attack airplane. There was also a Beech-18/AT-11 and some stuff from Lockheed as well, but again, these were exceptions to the rule, all of which are explainable for their own unique reasons, and all of which are quite a bit smaller than the planes we're talking about. The point is, as a general rule, a larger World War II bomber, medium or above, would not be a low wing if it was using that twin tail design. So why not? What's going on here? Well, it has to do with stability, primarily lateral stability about the longitudinal axis, and that means stability in the roll axis. We can see in this image from Pilot's Handbook of Aeronautical Knowledge that there are several factors contributing to this type of stability, and the first one is dihedral. Dihedral means that the tips of the wings are higher than the roots. When in stabilized, straight and level flight, if a wing drops, the plane will start to slip sideways through the air towards the low wing. We don't want that. We want our plane flying straight through the air like an arrow, or an idealized arrow anyway. So there are a lot of design factors built in to keep the airplane flying straight like an arrow, and one of those things is dihedral. Switching over to Aerodynamics for Naval Aviators, aka AFNA, because that book has better descriptions of these factors, we can see that dihedral is a powerful contributor to stability. Now, it's a common misconception that dihedral will always keep the wings level relative to the surface of the Earth. It does nothing of the sort. What it does is raise the windward wing during a slip. Now, if the plane was in straight and level flight with the wings parallel with the surface of the Earth, and a wing drops, then dihedral will tend to return it to straight and level because the angle of attack will increase as the plane on the windward wing as the plane slips and cause that wing to rise. However, if the plane was in a constant bank descending turn, it will try to return it to that state. What's important to understand here is that dihedral only has an effect when the plane is in a slip, and that is very clearly spelled out in AFNA, and it's often misunderstood in aviation, even among pilots. Now, the position of the wing on the fuselage also has a large effect on lateral stability. A high-wing airplane has an advantage here. In fact, a high wing by itself is worth about 5 degrees of dihedral. Now, that matters because with all other factors equal, less dihedral is better for performance because more of the wing's lift is in the direction that opposes weight. Thus, a high-wings airplane to get away with less dihedral offers a small performance advantage. The B-17 with its low wing has 4.5 degrees of dihedral. I couldn't find that specification for the Lancaster, but just looking at it, it appears to have about the same amount, even though the B-17 is disadvantaged in terms of stability by its low wing. Well, the reason has everything to do with those tail designs. The vertical surfaces of the tail contribute to this in much the same way as dihedral, as shown by this diagram from AFNA. The aircraft rolls around its longitudinal axis, which runs through the center of gravity. So when the vertical surfaces are well above the center of gravity and the plane is in a slip, they have a very strong effect here. Let's talk about sweepback just for a moment because it's in the diagram. This is a diversion because it's not much of a factor in World War II bombers, a little bit in some, and it does have an effect here. If you have a high-wing airplane with a large vertical tail and swept wings, you may run into a situation where the plane becomes so stable it's a problem. The pilots do need to be able to slip the airplane in some situations, particularly crosswind landings. That's the reason you see certain military transports with no noticeable dihedral, or even with anhedral, which is the opposite of dihedral. Back to our bombers. So the B-17 has a low wing and not a lot of dihedral. It's getting its stability from that oh my god Becky tail. This is probably Sir Mix-a-Lot's favorite bomber. However, there's a big drawback to a large tail. First, it adds a lot of drag, so the B-17 pays a big penalty there. Second, it interferes with the upper turret's field of fire. That's an advantage of the Lancaster's design. Its wing position allows for a relatively small amount of vertical tail surface, helping to reduce drag. Furthermore, of the vertical tail surface it does have, it doesn't need to be all that much above the center of gravity. So they can position those surfaces outboard and fairly low on the airplane, keeping them largely out of the upper turret's field of fire. And on the Lancaster, that's exactly what they did. Now, I'm not saying that this configuration is unique to the Lancaster. There were other planes configured in a similar fashion and for similar reasons, but right now we're talking about the Lancaster. The Lancaster's wing position also factors heavily into one of its most famous features, its bomb bay. The lack of wing structure on the floor of the plane gave the designers more of a free hand in that area. They built a very strong floor which also served as the roof of the bomb bay, allowing for very strong attachment points. And it's a long bomb bay, 33 feet long and about 5 feet wide. It's not very deep, meaning the bombs can't be stacked one on top of another. They have to be set up side by side and fore and aft. The bomb bay was wide enough to have 3 1,000-pound bombs side by side, and they could put a total of 14 of them in there. That was the maximum bomb load for a normal, unmodified Lancaster. That doesn't mean Lancasters always carried that much. They often flew with less, but the maximum bomb load was 14,000 pounds. For comparison, the maximum internal bomb load of a normal production B-17F was 12,800 pounds, and for the B-24 it was 13,200 pounds. So in both cases the Lancaster could carry more, although not as much more as most people think. The idea that the Lancaster has 2 or 3 times the payload capability of a B-17 is just a myth based on apples to oranges comparisons. Now, range with those loads is another issue, and we'll get to that. I have put the manuals for all of these planes in the Patreon section. The Lancaster and B-17 manuals are available at the lowest level tier. The B-24 and other British bombers that seem to be largely forgotten, like the Handley Page Halifax and the mighty Short Stirling, those manuals are at the higher tiers. The design of the Lancaster's bomb bay was easy to modify for odd size and shaped payloads, as there was no significant structure in the area below the aircraft floor, largely because of the wing location. Thus, they could modify the plane by altering, enlarging, or removing the bomb bay doors. They could add fairings and do all sorts of things. Of course, the plane would then take a big performance hit, but this could allow it to take special weapons a standard Lancaster couldn't carry. Regarding the bomb bay, it seems most discussions on YouTube and in the History Channel type documentaries always mention the size of the bomb bay and then just stop there, as if that alone makes it the end-all be-all of bomb bays. Well, there's no free lunch. All of these things are a series of compromises, and the Lancaster is not immune to this. Its bomb bay has some real drawbacks. First of all, it's not accessible by the crew in flight. Thus, in normal usage, bombs have their pins pulled before takeoff to allow the arming vane to spin during the fall to Earth. If the crew needs to jettison the bombs over friendly territory, that's not good. There was a small inspection port through which the bombardier could shine a flashlight, but if something was amiss, there wasn't a lot he could do about it. By contrast, the B-17's bomb bay, like most other heavy U.S. bombers, was accessible in flight and had a narrow internal walkway. Thus, the bombardier could access the bombs in flight to pull those pins, which was the normal procedure, usually done when the plane was no longer over friendly territory. Another issue was the possible failure of some bombs to drop. That issue affects any bomber, but it's a bigger deal in the Lancaster because of its inaccessible bomb bay. The bomb release mechanism was heated to prevent it from freezing up, but sometimes it failed to operate, resulting in a bomb that didn't drop when commanded, and could then later drop onto the closed bomb bay doors and be rolling around freely in the airplane. Now, the pin for the arming vane was already pulled before takeoff, and the falling of the bomb would pull a secondary pin, so the bomb is pretty close to fully armed at this point. Various books on the Lancaster have stories about this exact scenario, and they all sound pretty frightening. In the B-17, the bombardier could just go back there and fix the problem, so the bomb would release, or, worst case, pin it so it can't arm and secure it so it can't fall. The last drawback of the bomb bay is the time it takes to load it. There are 14 bomb stations, and a manually powered winch or hoist was used to raise each bomb into position and attach it. That hoist, which weighs 112 pounds, has to be relocated manually to each station before the bomb is lifted into position. So it's a time-consuming and manpower-intensive process, more so than in other airplanes because the shallow bomb bay doesn't allow the bomb to be stacked vertically, and the hoist has to be moved for every bomb station used. So when we talk about the large bomb bay, it's important to keep in mind the drawbacks and dangers the crew had to deal with. If we just say big bomb bay and stop the discussion there, we're discounting the bravery and efforts of the crews that had to deal with these drawbacks. In terms of aircraft design, the greater point, I suppose, is that yes, the bomb bay was large, and that was a big part of the reason the Lancaster could carry that payload, but there was a cost associated with that. Moving on to other things, the flying qualities of the Lancaster were very good. I don't think I've read a single negative comment about the way the airplane flew from those who flew it. It's not going to outmaneuver an FW-190 in a dogfight. That's not going to happen, but it was apparently quite pleasant to fly, had responsive controls and an easy-to-use and effective trim system and a pretty well laid out cockpit. The U.S. tested 2 Lancasters during the war, and the reports on the flying characteristics are in line with what the British pilots said. The report is full of superlatives when describing the plane's handling in the air, placement of the controls, and visibility from the cockpit. I want to point out I'm using multiple sources for this video, Aerodynamics for Naval Aviators, Pilot's Handbook of Aeronautical Knowledge, some official stuff from the U.S. military during the war, but additionally I'm leaning pretty hard on McKinstry's 585-page book. I'm using it for this quite a bit. I don't normally use these secondary sources, but his book is very well researched, and every source that he has listed that I looked into has checked out, so I have quite a bit of faith in this book. There are quite a few good books on the Lancaster, but this particular one has a lot of information, and it's presented very well. Every page is exciting to read. Now, let's talk about the Lancaster's defensive firepower. Very early Lancasters had 4 powered turrets with a total of 10 .303-inch machine guns, 4 in the rear turret and 2 in the others. The lower or ventral turret is located just aft of the bomb bay. It's too small to put a man in it, so it's operated via a periscope. It was eliminated from these planes pretty early on, sometime in 1942. There are several reasons for that. First, periscope-operated turrets on operational airplanes were very new, and they didn't get it just right with this initial attempt, which is understandable. It moved too slowly, and the field of view from the periscope was too narrow, only about 20 degrees, and that just wasn't enough to allow the gunner to use the turret effectively. For comparison, the gunner's periscopes in an A-26 have a 70-degree field of view and were incredibly effective, so much so they could reliably hit enemy aircraft at 1,000 yards, far beyond what a B-17 turret gunner could do with the same 50 caliber weapons. However, the A-26 is a late war airplane with a late war, very advanced turret system. Rather than try to improve the Lancaster's ventral turret, they just eliminated it. The logic being that it wasn't needed, it added 500 pounds of weight to the airplane, cost 10 miles an hour of airspeed, and probably most significantly, added a lot of expense and time to the plane's production. It's hard to Monday morning quarterback this one. On one hand, it did leave the Lancasters vulnerable to attacks from below, and this was exploited by German fighters. On the other hand, most of its missions were at night, and I'm not sure that turret would have been effective at night. Maybe it would have, I can't really say. I'll leave that one to be discussed in the comments section. I'm curious to hear what you guys think about that. Perhaps a bigger issue and a bigger problem was the decision to use the British .303 machine gun for the Lancaster's defense. Now, this was a bureaucratic decision that took place years before the Lancaster's first flight, but due to bureaucratic momentum, plus all of the problems associated with wartime production, the vast majority of Lancasters soldiered on with these guns until the end of the war, which is a shame because the British did have what was probably the best air-to-air gun of the war, which was their 20mm cannon. It was considered for use in the Lancaster, but the idea never went anywhere. So the standard Lancaster defensive armament became 8 .303, or roughly 30 caliber, machine guns. 2 in the front turret, 2 in the upper turret, and 4 in the rear turret. That left some big unprotected gaps in coverage. Worse, the guns just weren't effective, as we'll see later. All 3 of these turrets were hydraulically powered. At the moment, I'm talking about a standard or normal Lancaster. There were some variations I'll get to. The forward turret got hydraulic power from a dedicated pump on the inboard right engine. You lose that engine, you lose power to that turret. I want to stress that these turrets were powered by dedicated hydraulics. That pump is not tied into the airplane's main hydraulic system. The upper turret, which was usually a Fraser-Nash unit, was powered by a dedicated pump on the outboard right engine. The tail turret was powered by a dedicated pump on the outboard left engine. One of the things to consider here is that if you lose an engine, you lose power to its corresponding turret. By contrast, the B-17 had hydraulic power for the upper and lower turrets. However, those used local hydraulic systems and were powered by the plane's electrical system. As the B-17 had an electrical generator on each engine, loss of an engine did not mean loss of turret power. The B-17G model has an additional turret in the chin which is driven electrically. The turrets in the Lancaster and the B-17 and most other airplanes did have manual backups, so the gunner could still move them without hydraulics. However, all accounts I have read in regards to both British and US turrets indicate that manual backup was pretty difficult to use. The turret couldn't be traversed fast enough to accurately track aircraft. You had to position it and wait for the enemy to fly into the sights. Some late war Lancasters used a US-designed Martin turret. This was powered by the plane's electrical system, no hydraulics involved. I've put the manual up for it in the Patreon section. It features twin 50 caliber guns, which were far more powerful than the 303s. Still not a 20mm, but good enough. Martin designed the turret with some serious armor protection for the gunner. It's about a 1/2 inch or 13mm thick. This turret alone probably has more armor than the entire Lancaster with the more common Fraser-Nash turret. The downside was, of course, weight. It was so heavy that it had to be placed farther forward on the fuselage. Not too many Lancasters were built this way, but you can usually recognize them because the turret is forward of the roundel, assuming it's painted on the side of the fuselage in the normal location, and the turret is normally aft of the roundel with the Fraser-Nash units. Both turret types are visible in this picture. I want to mention that The website for the Bomber Command Museum of Canada has some really good information on the upper turret configurations, and they have a Lancaster with the Fraser-Nash turret, and it's in the Martin turret location, which is pretty interesting. I'm sure there's some interesting story there. Judging from their website, it looks like these folks are doing fine work up there, and they also have a Martin turret on display, so that's pretty cool. Back to the Lancaster. In the rear, we have a powered turret with quad 303s supplied with a massive 2,500 rounds per gun. There was so much ammunition that to keep the plane in balance, they had to locate the ammo near the upper turret, and then they used a fairly clever mechanism to deliver it aft and feed the guns. Apparently this mechanism worked very well. I haven't read any reports of jamming issues. However, there were other problems. It was very difficult for the rear gunners to see enemy fighters at night. They tried removing the perspex from the rear of the turret. Perspex is a transparent plastic like plexiglass. That helped, but it wasn't enough. Some Lancasters had the Rose turret packing twin 50 calibers. That was a good upgrade over the quad 303s. Notice in this picture the perspex is cut away. The problem of not being able to see Luftwaffe night fighters until it was too late was a big deal. The solution to counter the night fighters was the Fraser-Nash FN-121 turret, often called the Village Inn or ALGT for automatic gun laying turret. This had built-in radar that could detect enemy aircraft and even aim and fire automatically. The automation was rarely used, not because it didn't work, but because there were a lot of friendly aircraft that didn't have IFF or identify friend or foe equipment. By this stage of the war, just due to the relative numbers of Allied and Axis planes, the likelihood of a friendly fire incident with an automatic system like this was pretty high. Thus, it ended up being used mostly as an early warning system, and then the gunner would still fire the guns. However, even that method had its drawbacks, as the German planes figured out they could home in on the unit's radar. Of all these configurations, I think a best-case Lancaster would have been with a Martin upper turret and the FN-121 in the rear if operating at night, or for daylight, the Rose turret in the rear. In practice, the vast majority had the earlier triple turret setup with 8 303s all the way around until the end of the war. These were largely ineffective, and it didn't take the Germans long to figure this out. In April of 1942, Lancasters were sent out on a daylight raid into Germany. At this stage of the war, there were military leaders in Britain, and certainly in the United States, that believed that unescorted daylight bombing could work out, so that's what they tried. Keep in mind that at this point, the RAF had been bombing the Reich at night for 2 years with seemingly little effect, so there was an argument to be made for at least trying daylight bombing. The ineffectiveness of these early war night raids are discussed at length in McKinstry's book. Now, later in the war, this would change due to new equipment and tactics, and I'll get to that. The target they chose for this daylight raid was Augsburg. The plane to be used was, of course, the Lancaster. Augsburg is pretty deep into enemy territory, but it was thought that if by flying in low, the Lancasters could avoid detection, and if they did encounter enemy fighters, that their 3 powered turrets with the 303s could hold them off. Augsburg was chosen more due to politics than for practical reasons. Some in the Royal Navy were arguing that the Lancaster should be used on the Atlantic side to help them out. Bomber Command wanted to use them over the continent. Thus, Augsburg was chosen because it could satisfy both of them. The target there was a factory that built U-boat engines, so destroying it would help out the Royal Navy and showcase the Lancaster's effectiveness as a daylight bomber over continental Europe. 12 Lancasters went out, each with a 4,000-pound bomb load. If that payload sounds light for a Lancaster, keep in mind this is a daylight raid far into enemy territory and quite a bit of the flying at low level. Taking 14,000 pounds was not an option in these conditions. An attempt was made by Douglas Bostons with fighter escort to draw the Luftwaffe away from the areas through which the Lancasters would pass. Unfortunately, through errors in timing, the Bostons, aka A-20 Havocs, flew their mission 40 minutes early, meaning that the German fighters were returning to their bases about the time the Lancasters went by. It's highly likely the German fighters were low on fuel at this point, possibly low on ammo, when they spotted one group of 6 Lancasters and gave chase. Led by a 100 victory ace that had been flying in combat since the Spanish Civil War, the Luftwaffe fighters quickly overtook the Lancasters. They were hesitant to attack at first. This was the first time German fighters had encountered Lancasters, and the pilots were not quite sure of what they were facing. They started with probing attacks and quickly realized that the Lancasters only had 303s for defensive fire. And German pilots were well aware of the 303's capabilities, and they knew its effective range was much less than that of their own 20mm cannons. They stayed out of range of the 303s and pummeled the Lancasters with 20mm. They started firing at about 700 yards, broke off aggressively around 400 yards, thus staying outside of the Lancaster's effective envelope of defensive fire. They made quick work of the Lancasters, shooting down 4 of them before turning back. I suspect the German fighters broke off the attack because they were low on fuel, possibly low on ammunition. We do know that no German fighters were shot down. The remaining Lancasters reached the target. Some were lost due to anti-aircraft fire, but they did put 17 1,000-pound bombs on target. That's impressive flying, but only 12 of those bombs detonated. 7 out of the 12 Lancasters were shot down. Of the 5 that made it back, all of them were damaged. 1 of them was a total loss. The damage to the manned U-boat engine factory at Augsburg was minimal. The raid had almost no effect on production, as most of the tooling was undamaged. Most of the destruction was of non-essential stuff like building walls and the like. So by any objective standards, the raid was a failure, but in practical terms, it sort of worked out. Churchill turned this into a propaganda win, and the flight leader Nettleton, seen here second from the left with his crew, was awarded the Victoria Cross. He's seen here autographing a factory worker's photo. It said that she worked on the very Lancaster he flew in the Augsburg mission, so this photo was part of the propaganda operation. The British took full advantage of it, which makes sense. The real significance, though, of the Augsburg raid for the Lancaster is that it made it very clear that it wasn't suitable for daylight bombing. In their first encounter with the Luftwaffe, the German fighters had no problem figuring out how to attack them with impunity, something they couldn't do against bombers armed with .50 caliber. Don't get me wrong, they could still shoot down the more heavily armed bombers, but they usually took losses doing it, and that's a big difference. Regarding the Augsburg raid, clearly a 58% loss rate was unsustainable. So the British changed tactics and started working on improving their night attacks. That's all for part 1. We still have a lot more to cover. I want to talk about the plane's hydraulics and electrical system, as well as the specialized equipment that made those later night attacks more effective. Some of that stuff is really interesting. I also want to get into the range versus payload issue. That's an area where the Lancaster shines. And of course, I'll cover other performance aspects as well. I want to thank my subscribers and especially my Patreon supporters who make this channel possible. Patreon supporters often get early access to videos and, of course, access to aircraft manuals and other period documents used in the creation of videos on this channel. That's all for now. Goodbye and have a great day.